we're going to do some accumulation problems. So let's suppose that a of t is equal to 0.15 t squared plus b. We make an investment of $400 at t is equal to 1. And what is the total amount of the investment that we have at time t equals to 9? Well, we have a of t is equal to 0.15 t squared plus b. So we should probably figure out what b is first. Now, what we know for any accumulation function is that the accumulation at time 0 should be equal to 1. So if we put in 0 for t in our formula, we're going to get 0.15 times 0 squared plus b. This right here is just going to go to 0, which will end up telling us that b is equal to 1. So our formula is really going to be a of t is equal to 0.15 t squared plus 1. So now that we have that information out of the way, let's clear up some space. And what do we know now? Well, if we know what the value of A1 is, the amount at time 1, we know that this is equal to the principal investment multiplied by the accumulation function at time 1. Now, we know what the accumulation function at time 1 is. This is just P0 times 0.15 t squared. When we put 1 into t, will just be 1. So it's 0.15 plus 1, which means that a of 1 is going to equal to 1.15 times our principal investment. But what is our principal investment? It's not $400 because we're looking at t is equal to 1. We need to find it as t is equal to 0. So what we do know is that A1, 400, is going to be equal to P0 times A1. So that's basically going to say that P0 is equal to 400 divided by 1.15. Now, I'm going to leave it in this form because I'm going to stick it into a calculator afterwards, and I don't want to lose any decimals for this example. So we have some information now. We know what P0 is. We know what B is. So let's ask ourselves, what is the accumulated value of the investment at time t is equal to 9? So in other words, we have to find big A of 9. Well, this is just going to be equal to P0 times little a of 9, our accumulation function. So we know what P0 is. It's going to be 400 divided by 1.15. And we also know what our accumulation function at time 9 is. It's going to be 0.15 times 9 squared plus 1. So if we put this into a calculator, what we're going to get as a final result is approximately $4,573.91. Okay, so this is a pretty big jump. We're investing $400 at time 1 to get $4,600 roughly at time 9. But this function is going to scale up quite quickly because we're looking at a quadratic and we're looking at 0.15 t squared, which would be basically 15% interest in the first year. So that's going to get large quite fast. Now, in general, we're able to use a little trick if we know the amount at 1 time and we know the accumulation functions at 2 times, then we can get the amount for that second time as well. And in other words, what I mean here is if we have little a of n, little a of m, big A of n, and big A of m, we have at least 3 of those, then we're able to find the fourth value. And the general formula is that big A of n is equal to the accumulation function for n divided by the accumulation function at time m, all multiplied by the amount at time m. Now, why is this? Well, this is because our principal is going to be the amount at n divided by the accumulation at n. Now, why does this work? Well, because if we take the amount at n, that's just P0 times the accumulation function at n. So if we divide both of these by the accumulation function at n, we're just going to be left with P0 out. So P0 is equal to the amount at n over the accumulation function at n. And it doesn't matter which times you take, so you can also do this with A of m and little a of m, whatever times those are, and they'll be equivalent. So we can just take this bit of the formula and do some cross multiplication in order to get what we need to get. So let's try a problem like that with a new accumulation function. So let's suppose that a of t is equal to at squared plus 1. We make an investment of $200 at t equals 0, which accumulates to $400 at t is equal to 5. So we need to figure out what a is. that would be pretty nice. So we know that the amount at time 0 is equal to $200. And we know that the accumulation at time 0 is just going to be 1, since little a of 0 is always 1. We also know that a of 4 is going to go, sorry, not a of 4, we're looking at $400 at time 5. So the amount at time 5 is going to be 400. This means that because we have 3 out of these 4 values, we're going to be able to find little a of 5. So let's just take a look at the original formula. So a of n over little a of n is equal to big A of m over little a of m. And we want to find essentially a5, little a5. So if we do some cross multiplication, what we can get is little a of m is equal to big A of m multiplied by little a of n, and divide that by big A of n. So the amount at m multiplied by the accumulation function at n divided by the amount at n. Now, okay, we can now put in some values for what we want to find. So we want to find little a of 5, the accumulation function at 5. And this is going to be equal to, well, big A of 5 multiplied by little a of 0 divided by the amount at time 0. And if we think about this, the amount at time 5 is 400. The accumulation function at 0 is always going to be 1. And the amount that we had at 0 was 200. So little a of 5 is just going to equal 2. So we now have our value here. Now, why is this useful? Well, because now we can figure out what our a value in our function is. So we know that a of 5 is equal to 2, and this should be the same thing as a times 5 squared plus 1, which is just the same thing as 25a plus 1, which means if we do some rearranging here, we're going to get 1 is equal to 25a, which means that 1 over 25 is going to equal a, which is the same thing as saying 0.04. So now that we have that value, we have our new accumulation function. This is going to be a of t is equal to 0.04 times t squared plus 1, which means that we can now work with the final question, which is to find the accumulated value at time t equals 15 of $500 invested at t is equal to 4. Okay, so what is this telling us? This is saying that big A of 15, well, we don't know it yet. We do know little a of 15, our accumulation function. This is just going to be 0.04 times 15 squared plus 1, where we put in 0.04 for a and we put in 15 for t. We can simplify this a little bit now. So this is going to be 0.04 times 15 squared, which is 225, and then we're going to add 1 to it. So this is 10. Now, in terms of our other information, we know that big A of 4, the amount that we have in, is going to be $500. And little a of 4 is going to be 0.04 times 4 squared plus 1. So that's just going to be 16 times 0.04. And 16 times 0.04 is 0.64 plus 1, which is going to be 1.64. So now that we have 3 out of our 4 values at these times, we can figure out what big A of 15 is. So we can just use the formula above. So big A of 15 is going to be little a of 15 divided by little a of 4, and then we're going to multiply this by big A of 4. So if we put in our values, this is going to be 10 divided by 1.64 multiplied by 500. This is the same thing as saying 5,000 divided by 1.64, which is going to give us approximately $3,048.78. So we invest $500 at t is equal to 4 with our accumulation function. We're going to have $3,050 roughly at time 15. So this is a very useful little trick. I mean, it's not really a trick. It's more just so using the fact that Our principal investment is basically our scaling function. So when you take the amount divided by the accumulation function, you just get your scaling function back. And we can use that information to manipulate two things. What about this problem? An investment is earning compound interest. Okay, so we got to remember our formula for compound interest. That means that little a of t is going to be equal to 1 plus our interest rate raised to the power of t. Okay, so if $150 is invested at year 3 and it accumulates to $200 by year 5, how much will $500 invested in year 7 be worth in year 12? Okay, let's figure out what we know here. We know that big A of 3, our amount at 3, is going to be $150. And because we know our function for compound interest, we can put little a of 3 in. That's going to be 1 plus I raised to the third power. Now, we don't know what the interest rate is, and we don't know what little a of 3 is at this point, but that's okay. We can keep going. We know also that the amount in year 5 is going to be $200, and little a of 5 is going to be 1 plus I raised to the power of 5. Again, that's just putting in the formula for compound interest. Okay, so what we can do at this point is we can play around with some things, I guess. What would be kind of useful is if we could figure out what the interest rate was. That would actually be super helpful. So what do we know about that? Well, we know that big A of 3 divided by little a of 3 is going to be equal to our amount at times 5 divided by the accumulation function at time 5. So if we mess around a little bit, we know that the accumulation function at time 5 divided by the accumulation function at time 3 is equal to the amount at time 5 divided by the amount at time 3. So just did some cross multiplication on the formula above in order to get this rearrangement in the other direction, but okay. So what are we going to do in this case now? Well, we can start putting in some values. So A5 is 200, we're dividing A3, which is 150, and this is going to be equal to 1 plus I raised to the 5th power divided by 1 plus I raised to the 3rd power. Now, we're going to get some cancellation here. So we have 1 plus I to the 5th on top, 1 plus I to the 3rd on the bottom. So what this is going to simplify to is 1 plus I squared on the left. And then 200 divided by 150 is just the same thing as 4/3. So what we can do now is we can take the square root of 4/3, which is going to be equal to 1 plus I, and we can now subtract 1 from the right side in order to isolate our interest rate. So our interest rate is going to be the square root of 4 divided by 3. We can put this into a calculator, and then we're going to subtract 1, which is approximately 0.1547. Okay, so now we have our interest rate, which is fantastic. So we can start looking at the rest of the question. It's a lot of work just to get an interest rate, but we don't need any of this information anymore. So we'll delete all of that, and we'll remind ourselves that the interest rate is equal to 0.1547. Okay, so what this means is that we're investing $500 in year 7 now. We want to know how much that'll be in year 12. Okay, so A of 7, the amount at 7 is equal to $500. The accumulation function at time 7 is going to be equal to 1 plus our interest rate, which is 0.1547 raised to the power of 7. And let's just get this to be kind of a nasty little number that we can use. We really should be keeping this in a graphing calculator or in a financial calculator, so that way we don't lose decimal places. However, this is just a little video, so we'll cut some of these off. So 2.7371. Okay, now we need to know how much $500 invested in year 7 will be worth in year 12. So we need to figure out what A of 12 is, but we do know what little a of 12 is. because this is just going to be the same thing as a 7, but we're raising to the power of 12. So 1.1547 raised to the power of 12. And what is this going to be? Well, just change that in our calculator, and that's going to be 5.6186. Okay, so now we have some numbers. We want to find what A12 is. So this is going to be equal to the accumulation at 12 divided by the accumulation at 7 multiplied by the amount at 7, which is just going to be 5.6186 divided by 2.7371, and then we're multiplying it by our amount, which is $500. So if we put this one into a calculator, so we divide that by 2.7371, we multiply it by 500. What is our final value? That is going to be $1,026 and roughly 38 cents. So if we put in $500 in year 7, we're going to get 1,026 back out in year 12 with a compound interest rate of 0.1547 or 15.47%, which we obtained by playing around with the amounts and accumulations in year 3 and year 5. So this one was a little bit more involved, but it's really just about taking what you know, plugging in the formulas, plugging in the numbers, and then manipulating them to get a result. So here's a general shortcut from what we saw earlier. So if we have an amount AM at time M and a compound interest rate of I, then we can find the amount at N at time N using the following equation, because basically, if we take a look at our old formula, big A of N is equal to little a of N divided by little a of M multiplied by big A of M. In terms of compound interest, this is basically going to be 1 plus I to the N divided by 1 plus I to the M, which is the same thing as 1 plus I to the N minus M. So really all we've done in this place is just replaced our accumulation function with 1 plus I, and then we've done the algebra already. So here's the final problem we'll take a look at. An account earns interest at an effective annual interest rate of 5%. The account balance is 300 at t is equal to 3. What will the balance be at t is equal to 6? And what was the original balance? Okay, so I'm just going to write some stuff out so I have it. So I is equal to 0.05. The amount at 3 is equal to 300. Little a of 3 is going to be, well, that's going to be 1 plus 0.05 cubed. We want to find the amount at time 6, and we know the accumulation function at time 6 is going to be 1 plus 0.05 to the 6. Okay, so using our formula from above, the amount at time 6 is going to be, well, let's use our little shortcut here. This is going to be the amount at time 3 multiplied by 1 plus 0.05 to the 6 minus 3. So this is going to be the same thing as saying 300 times 1.05 cubed. And what's that going to get us? Well, we can go to our handy dandy calculator here, 300 times 1.05 to the power of 3, which is going to be 347 and 29 cents. Okay, so that is big A of 6. Now we want to find the original balance as well. So what is the original balance going to be? Well, that's just going to be the amount at time 0. So if we do the same thing as before, we know that the amount at time 0 is just going to be, well, we can pick any of these here. So let's pick big A of 3. Then we're going to multiply that by our interest rate, which is 1.05. Now we need to do 0 minus 3 because we have our n, we have our m. And this is going to be the same thing as 1.05 to the negative 3. Another way we could write this is the amount at time 3 divided by 1.05 cubed. So this will get us our original amount. So if we put in big A of 3, which is going to be 300, we can divide this by 1.05 cubed, which will give us a total of $259.15. So at time is equal to 0, we put in 259.15 or $259.15 with an annual compound interest rate of 5% that grows to 300 at time 3, and then at time 6 that grows all the way up to 347.29. So hopefully that wasn't too bad. Again, this is just playing with the stuff that we learned earlier, playing around with formulas a little bit, and getting comfortable with writing out information and figuring out what we need to figure out.